Okay, so I haven't seen another person joining for a minute or two, so let's just assume we have reached a steady state. Okay, on this afternoon, there's more about BMS and numerical relativity on the program, and I'm happy to welcome Keefe Mitman here as a speaker. Keefe is a graduate student at Caltech working in the simulation extreme spacetime collaborations. I'm also a member, and he's the person actually responsible for quite a few of the results that I was briefly touching on in my talk last week. And so I'm very grateful for Keefe giving this talk on short notice to follow up and deepen what I was only having time for 5 minutes to talk about last week. Okay, Keefe, please take it away.
Okay, can you hear me all right?
Yes.
Mm-hmm.
Okay, yeah, so thank you, Harold, for that introduction, and thank you to the organizers for inviting me to speak at this workshop. As Harold said, this is kind of a follow-up to some of the work that he was discussing, but hopefully I'll be going into things in much greater detail. And also, right, I'm a bit of a last-minute addition to this workshop, so if I cover things that have already been covered, forgive me. I'm just going to try to be as thorough in my explanations as I can be. So today I'll be talking about gravitational memory in numerical relativity. More specifically, I'll be talking about how we can compute memory effects from our waveforms, how we can use these memory effects and the BMS balance laws to correct certain waveforms that are produced by our collaboration. And then I'll also talk about how the memory makes the BMS frame of our waveforms very important. And I'll get into kind of what all this means in a little bit more. And then last, I'll kind of just wrap up with some estimates and overview on the detectability of memory and kind of what we can look forward to in the future with current detectors as well as future detectors. But kind of like any talk on gravitational waves, I'm actually just going to start by showing kind of what got this whole thing rolling. The first detection that was made, right? So this is the plus polarization of the waveform seen by LIGO for the event GW 150914. And this is a waveform produced by a full numerical relativity simulation. So this should be exact in terms of general relativity. And as you can see, it's pretty much what people typically think of when they think of a gravitational wave, and is what many people throughout this conference have been showing during their talks. There's an inspiral phase, a merger phase where the frequency increases, and then a ring down phase where we see these this excitation of the quasi-normal modes due to black hole perturbation theory. But at this point, I just have to apologize on behalf of all numerical relativists because this is incredibly misleading. And this waveform is not at all correct according to what we would expect from general relativity. Instead, we expect waveforms to have memory. And here I'm showing what the true waveform should have looked like for GW 150914. So when we usually think about memory, right, throughout this conference, memory has been talked about in terms of supertranslations, and we typically think of it as this DC effect, where it's this zero frequency contribution arising from these symmetries at asymptotic infinity. And in a more practical context,
are you really saying it's like a 20% effect of the maximum amplitude?
Right, so I will note that here I've oriented the binary to produce the maximal memory effect. So the actual effect you would have seen in GW 150914 is about 40% of what's shown here. But it is much larger than previous expectations that have only used analytic techniques. And so I can get into this a bit more later on when I show some more estimates on what the memory is that we should see.
I mean, analytic techniques are very simple for calculating the memory, right? You only need the ingoing and outgoing for momenta. So what you're saying the numerics disagrees with the analytic calculation?
No, I'm saying, right, so previously when people give us estimates of the memory we should see for these binaries, they're either using post-Newtonian theory or they're using what's called a minimal waveform model, which is when you compute the memory from other modes of your waveform. But that's still approximate. It's not a true value. And so when you look at the memory from a waveform generated with memory, when you actually solve Einstein's equations, this is the effect you see. So it is larger than previous estimates.
So do you mean that most of the memory comes from the merger phase, which is not covered by the PN approximation?
Right, right. And that's where this minimal waveform model comes in. You take the other higher order modes of the waveform and you compute the contributions you would expect to the memory effect using certain equations that I'll talk about later on. But yeah, so maybe we shouldn't get too hung up on it now.
Well, it seems pretty important. You can't just use the Brzezinski-Thorne formula and take the incoming and outgoing momenta of the incoming moment of the black hole and the outgoing. I thought that was the beauty of memory.
Well, so that's what we typically call linear memory. For binary black holes, the memory we see is called nonlinear memory. In the earlier works of Christodoulou and Zeldovich.
So the Brzezinski-Thorne is a one.
Brzezinski-Thorne is an exact formula. Yeah.
And
I'm sorry?
Brzezinski-Thorne takes both of those, combines all those things.
Right, and so this is exactly that expression where you essentially are using the energy flux to give you the expected value of the memory. That's what I'm highlighting here in red. This is just the usual nonlinear memory formula for a gravitational wave.
What about the Brzezinski-Thorne formula? Does that agree with the numerics?
Yes, yeah, everything agrees with the numerics.
I have a question, very rapid. The offset at time 0 is due to the previous phase, or?
Right, so typically when we run these numerical simulations, they're finite in length. So the initial value of the strain will actually be around 0. Here I'm doing a special kind of frame fixing, which I'll get into later, where we essentially change the numerical waveform, we change its frame to agree with the frame of a post-Newtonian waveform. So the initial value of the memory that you see here is in agreement with what we would expect from a post-Newtonian waveform.
Thanks.
Mm-hmm.
By the way, here, do you have misaligned spins?
Yeah, this is exactly the same as GW1509-14. So I forget what the exact parameters were, but I'm sure that's just somewhere in the original paper.
It's not known exactly. It's one possibility. Yeah.
Right. Yeah. Yeah. But I can get into more about what memory looks like based on spin configuration later. This is mainly just supposed to be, look, this is what we should be seeing. We haven't seen it yet. Okay, but if people are comfortable moving on, then I can get into detail a little bit more. So just to kind of give a historical overview of memory, right? So it was first realized in the 70s by studying compact astrophysical objects traveling to asymptotic infinity as t goes to infinity. So this is one of the original formulas. So it was originally found by Zeldovich and Polnarev, and then this is one of the original formulas introduced by Brzezinski and Thorne. And so this is what I was talking about regarding linear memory, what in more modern day analyses is called ordinary memory. And so this corresponds to objects which are unbound from each other. So this is the type of memory you would see for, say, hyperbolic black hole encounters, or in a neutron-star merger when you have matter that's being ejected from the merger. M here is just the mass of whatever particle or source you have. B is the velocity of its center of mass. And then theta is just the angle between the velocity and the vector from the source to the detector. And so then what Christodoulou and Thorne realized is that a very similar effect occurs for null radiation or gravitons, and they called this the nonlinear. And so Christodoulou realized this by studying the Bondi mass loss formula. And then what Thorne did is he found that this equation by Zeldovich and Polnarev is really also works for gravitons. You just have to interpret this mass divided by this Lorentz, or mass times this Lorentz factor, as corresponding to the energy of the graviton. And so then Thorne presented this equation, which shows that the null radiation, which contributes to the null memory, can just be understood as this integral over the energy of the gravitons projected along this transverse traceless component. And so while this was really, really interesting, right, and it helps us understand this pretty surprising effect, memory kind of died away for a few decades, and then was recently brought back to interest by some of the work of Andy and others who kind of introduced this infrared triangle. And so to talk about memory in a more modern context, it's really best to talk about the symmetries of asymptotic infinity. And to do so, we really have to talk about the work of Bondi, Vandenberg, Metzler, and Sachs, who realized that the symmetry group of asymptotic infinity is not just the Poincare group, but a group with a much more rich structure known as the BMS group. And so the BMS group, as I'm sure many people are aware, is just the semi-direct product between the Lorentz group and this group known of transformations called supertranslations, which contain the space-time translations as a subgroup. And so a pretty straightforward way to realize why supertranslations have to be symmetries in the first place is through the following thought experiment. If you have some group of observers surrounding some kind of event, and if you had enough information, even if the observers were receiving time or information from that event at different times, you could come up with a way to synchronize all of their clocks so that they could still discuss the physics that they're observing. But if you push these observers to asymptotic infinity, then performing such a clock synchronization becomes impossible, and we could freely time translate each observer without changing the underlying physics. And these direction-dependent time translations are exactly these supertranslations, with the kind of constant being the time translation, the supertranslations, which are represented by L=1 spherical harmonics being the space-time translations, and then the L = 2 or greater than 2 being what we call proper supertranslations, these more obscure direction-dependent time translations. And so this won't be as important for this talk, but I also just want to highlight that there's proposals for promoting the Lorentz group to be a much more larger group. And so the kind of two leading proposals for promoting the BMS group is the extended BMS group, where the Lorentz group is promoted to be local conformal Hilling vectors on the two-sphere. And this is pretty much the same as the Virasoro algebra. And this was put forth largely by Barnick and Trossert. And then a more recent proposal is this generalized BMS group, where we instead promote the Lorentz group to be local diffeomorphisms on the two-sphere. And so both of these are fine. We're kind of still working out which one seems to be the best choice, but they both resolve the kind of leading and subleading soft theorems and reproduce the typical BMS charges that we're used to seeing. But if you were to take these symmetries and try to use them to understand memory, kind of what you would start off by doing is you would just look at the metric corresponding to gravitational radiation. And so that metric is the Bondi-Sachs metric. And so here the details aren't too important. There's just a few functions that I want to highlight that are going to be important for some of the equations I present later on. So the first here in the angular part of the metric, QAB is just the round two-sphere metric. And this CAB, the strain tensor or the shear tensor, is the function that completely captures information about the gravitational radiation. The other functions I want to highlight is in the time component of the metric, this M, which is known as the Bondi mass aspect. And then in this function UA, there's this function NA, which is typically called the angular momentum aspect. And so if you take this metric and you apply your typical gauge conditions to place yourself in the Bondi gauge, and you work with Einstein's equations, you can essentially carry out the following procedure. So you first identify the BMS charges in this metric corresponding to these symmetries of the BMS group or the extended or generalized BMS group. You then apply Einstein's field equations as well as these gauge conditions to come up with evolution equations for these functions. And so typically the evolution equations you see are for the Bondi mass aspect and this angular momentum aspect. And then if you cleverly rearrange these equations, you can treat them as these balance laws, which essentially say that a change in a charge is balanced by a flux as well as a memory effect. And so this is what I'm going to be really focusing on today, is using these balance laws to study the memory effect. And so if you kind of just write these balance laws in a very simple way, what you obtain is the following. And so here I've kind of reordered things to be helpful for studying these effects in numerical relativity. And so this first balance law corresponding to supertranslations says that the real part of the strain can be written as a Bondi mass charge plus an energy flux. And the second balance law corresponding to what are typically called superrotations, this extension of the Lorentz group, this says that the imaginary part of the strain can be written as the retarded time derivative of an angular momentum charge and an angular momentum flux. And so what's really useful about these balance laws, apart from giving us this charge flux breakdown of the strain, is that they're very helpful for understanding memory. So an easy way to see that is by focusing on, say, the energy flux term. If we think about our typical binary black hole inspiral, we know that a large amount of energy is going to be radiated in the form of gravitational waves. So we would expect an energy flux term would kind of have some non-zero net change over time. And due to these balance laws, we would expect that this non-zero net change in the energy flux should be reflected in the left-hand side of this equation, in the real part of the strain. And so it turns out that actually each of these four terms corresponds to a different type of memory effect. So the terms for the real part of the strain, these are typically called electric memory due to them having electric type parity. And the terms in the imaginary part of the strain are typically called magnetic memory effects, again, simply because they have magnetic parity. And then again, relating back to these formulas introduced in the original work on memory, the memory associated to the charge terms is called ordinary, because it typically arises from unbound sources. And then the memory associated with these flux terms is called null memory. Okay, so then what exactly is memory physically? Well, the most common memory we're used to thinking of is typically what's called displacement memory. And so really this type of memory is the relative displacement between a series of observers that's induced by the passage of gravitational radiation. And so previously, we've typically assumed that these observers have to be initially co-moving. But it turns out that if these observers have some relative velocity or even a relative acceleration, then there can be additional contributions to this displacement memory effect. And so if the observers have a relative velocity, the terms contributing to the displacement memory effect are what we call subleading displacement memories. And this is the usual spin memory discovered by Sabrina, Andy, and Sasha, and the center of mass memory discovered by David Nichols. And both of these have been further extended and analyzed by Jeffrey in a great amount of detail. And so this usual displacement memory is what we typically associate with supertranslations. And then these subleading displacement memories are what we associate with super Lorentz transformations, or you can break those up into their two parity types. So super rotations for spin memory and super boosts for center of mass memory. And really another way to kind of understand these memory effects, if your observers don't have some relative velocity, is the spin memory will show up for observers in a counter orbiting trajectories, and the center of mass will be for any parallel trajectories. But for today, I'm primarily just going to focus on displacement and spin memory, because those are the two dominant contributions for binary black hole mergers. The center of mass memory actually can be noticeable for hyperbolic black hole encounters, but we haven't really seen those in our detectors, so I'm going to stray away from that today. So again, I just want to return to these four terms that I presented when talking about the balance laws. So if you like seeing equations, feel free to study these, but all I want to really highlight is that the balance laws say that the strain can be written as the sum of these four terms: a mass charge, an energy flux, an angular momentum charge, and an angular momentum flux. And so for each of these terms, you'll notice there's a series of angular derivatives or inverse angular operators acting on certain functions. These are just included to project things into a spin-weighted spherical harmonic basis, which is usually what we represent the strain in. But the main things that I want to highlight is just that this mass charge term is directly related to the bonding mass aspect. The energy flux term is directly related to an energy flux. The angular momentum charge is just this time derivative of this angular momentum aspect, which is dependent on the psi1 bioscalar. And then the angular momentum flux is this more complicated combination of the strain and the muse. And so what's great with this then is, if we run a numerical simulation and I give you a strain, the news, and some of the bioscalars, you can compute each of these terms and use them to study which mode of the strain is sourced by which one of these terms. Okay, and so just to give an example of what this looks like.
Sorry?
Yes?
Why is there a time derivative for angular momentum charge?
Right. So when you have these balance laws, the imaginary part of the strain is sourced by the time derivative of an angular momentum charge and an angular momentum flux. Sorry? So it's not that that Jn is really the angular momentum charge. It's related to the time derivative of the angular momentum charge. Similarly, this Jj term is related to the time derivative of the angular momentum flux. Okay, but to kind of give an example of where these terms provide their usefulness, here I just have the 2-2 mode of a strain waveform for an equal mass non-spinning system. The strain is in gray and it's kind of hidden behind this black curve, which corresponds to the body mass aspect. And all the other terms are just 0. And this shouldn't be too surprising because this body mass charge is really the mass moment, and the 2-2 mode being the dominant mode of the strain waveform, we would expect it to be sourced by the mass moment. And so that's kind of exactly what's happening here. Similarly, if you look at the next most dominant mode of the strain, the 3-2 mode, which is a magnetic parity mode, then this is sourced by this angular momentum-like charge. Again, it's very similar to what we see with the body mass charge in the 2-2 mode. Here, it's just the angular momentum charge because we expect this mode to be sourced by the current moment. And so then we say, great, right? We've seen these modes that are sourced by the mass charge and the angular momentum charge. What about modes that are sourced by these flux terms, which for binary black hole in spirals, we expect to represent these memory effects that we've been discussing? Well, based on post-Newtonian theory, which has largely been carried out by Mark Favada, we expect the memory to show up in the 2-0 mode. And so if we take a numerical relativity waveform and we plot the 2-0 mode, what we obtain is the following. And what you see is that there's these oscillations due to quasi-normal mode excitations, but there's no memory effect.
Sorry, what was the 2-0 mode?
This is the 2-0 mode should be the dominant memory mode, the dominant displacement memory mode based on post-Newtonian theory. So if there's memory in the waveform, this is where we should see it. And what you should be concerned about is that you don't see any memory. There's no overall net change in this mode, right? So you ask, where's the memory, right? This is clearly something wrong going on with the numerical relativity waveform, or we've largely misunderstood kind of how Einstein's equations work and where memory comes into play. With it more likely being that something's going wrong with numerical relativity waveforms. And it turns out that the reason we don't see memory in numerical relativity waveforms is because the way we create these waveforms is very naive. So when we run a numerical relativity simulation, the way this works is we essentially run a Cauchy evolution for these two binary black holes in some finite region of space-time. And as we're running this evolution, we collect all of the metric data as a function of the retarded time and angles on the two-sphere at a series of finite radius world tubes. And then with these finite radius world tubes, we then interpolate between various points to obtain a denser set of data near where this evolution has been going on. And then we fit this data to polynomials in 1/r and extrapolate that to r goes to infinity to obtain what we would expect the strain to be, namely just this component multiplying the 1/r part of this polynomial. But the key thing I want people to take away from that is we never actually solve Einstein's equations. And so while it's currently unknown why this version of waveform extraction doesn't produce memory effects, the leading theory is that memory in binary black hole mergers is fairly nonlinear. And for some reason, when we don't solve Einstein's equations and instead just use this extrapolation procedure, it fails to capture these nonlinear effects. Fortunately, there is a better way to do this waveform extraction, which should be pretty obvious, right? We should just solve Einstein's equations on these null hypersurfaces connecting our world tube to asymptotic infinity instead of running this extrapolation procedure.
So to see the memory effect, of course, you have to keep very careful track of your coordinate system, which is measurable data. And you're probably not working in Bondi coordinates, right? That would probably be,
Yeah, when we
that
do
would
this
probably be the
extrapolation,
worst possible way to set up numerics, right?
right? Yeah, so we essentially do coordinate transformations towards the end, and so this is approximately Bondi, but yeah, still not exactly Bondi.
Yeah, so probably you're just, yeah, you're probably just, your numerics doesn't stick in the BMS frame and would naturally adjust itself to, yeah.
Right, and so that there's certainly many possibilities for why this breaks down.
Yeah.
But as I was saying, right, there's obviously a better way to do this, and so this better way is given the name Cauchy-characteristic extraction. And so just kind of a basic overview of how this works. We take that same data on a metric, the same metric data on a world tube, and then we connect this world tube to asymptotic infinity using these null hypersurfaces, which I've labeled with sigma. And then if we're clever and we choose reasonable initial data for this first null hypersurface, we then use Einstein's equations to evolve them forward in time to obtain more accurate waveforms at asymptotic infinity, as well as all the Weyl scalars. And so if we go ahead and do this, it turns out that CCE and extrapolated pretty much are identical for the 2-2 mode, the next most dominant, the 3-2 mode. But if we look at the 2-0 mode, right, this displacement memory mode, what we notice is the following. So here, again, I have the strain in gray. I have the Bondi mass charge term in black, which again, this was what the extrapolated waveform looked like. And then in blue, I now have the energy flux contribution. And then the angular momentum contributions are still 0. And so as you can see now, when we run CCE, we do indeed capture this memory effect as seen through the energy flux term. And so we can really understand this memory mode as being a combination of an energy flux, which sources the memory, as well as these quasi-normal mode oscillations, which are sourced by this Bondi mass charge or this mass moment. Okay, so great, we've resolved the leading displacement memory effect. What about the sub-leading displacement memory effects? Are we capable of resolving those in numerical relativity waveforms? And for those, right, for this.
All right, what's this picture here? It looks like the memory is now huge compared to the oscillations.
Right, and it is in this mode. So the one thing to keep in mind is that
just for that mode.
This is an individual mode, and we've scaled out the distance between the source and the detector, as well as the mass of the system. And so typically the oscillations in the 2-2 mode will be larger when you compute the full waveform in a given direction. Yeah. So if we're looking at the sub-leading displacement memory effects, more specifically the spin memory, which we expect to be more prominent than the center of mass memory, you want to find a mode that's sourced by the angular momentum flux, this green curve. And so if you kind of just keep looking through the modes, eventually what you find is the imaginary part of the 3-0 mode. And so what you'll notice is that this is pretty similar to the 2-0 mode. We have a contribution from the angular momentum charge and the angular momentum flux, where the charge sources these quasi-normal mode excitations, and the angular momentum flux sources this more dominant contribution. But what's different here is that there's no overall net change. So there's no actual memory effect in this mode. And so this is something that's actually well understood. It turns out that for most common sources of gravitational waves, we don't expect there to be any magnetic memory. And this has largely been shown by Lydia Bieri, as well as Winnicor and many others. But what you can imagine is that if you took this mode and you integrated it with respect to time, then this bump function that arises due to the angular momentum flux would yield a memory effect in the time integral of the strain. And this memory effect in the time integral of the strain is exactly what we associate the spin memory effect to. So it's important to note that the spin memory effect and the center of mass memory effect are really memory effects in the time integral of the strain, hence why they show up at this sub-leading order in the displacement memory effect. Okay, and so this is really phenomenal. We can create these incredibly accurate waveforms that have the memory effects.
Sorry, so what you're saying is so interesting. I can't resist commenting, but the you know, the statement that there's a shift in the mode of the metric in Bondi gauge that's a coordinate dependence statement. We could find some other coordinate system because, of course, coordinate transformations which don't go to 0 to infinity are physical. They can be observed in experiments as being proposed, but you can still find a coordinate system in which you could find some other coordinate system in which some component of the metric, even for the displacement memory, went back to where it started. Similarly, for the spin memory, there are other coordinate systems in which the subleading component of the metric does have a shift. So it's not qualitatively different. Looked at in the right way, it's on the same footing as the displacement.
Right. So for example, if you have
what you're saying is absolutely correct, but
no, that's a very good point. And so, for example, if you have a processing system, then you will actually see a mixing of these contributions. And so then you'll see like a non-zero change in the mode sourced by the angular momentum flux due to this mixing. Right, exactly. Yeah, so that's a good thing to point out, indeed.
And one other thing I want to ask you, so if you put two black holes together, if you merge two black holes, you don't necessarily, you could do it in a very careful way so that not that much energy was radiated. But when you have two black holes out there, typically two black holes will have a huge angular momentum, and a lot of angular momentum has to be lost because of the Kerr bound. Somehow a lot of angular momentum has to be radiated away. So in most of these events, I think some fraction of order 1 between the far past and the far future, some fraction of order 1 of the mass is lost, but a huge fraction, I think, of the angular momentum has to be lost. And what?
Sorry, go ahead.
Because they start, because there's an R in the angular momentum, and they got to get rid of all that. So the spin memory is related to the total angular momentum flux, which there has to be a lot of for this reason. Did you see any kind of but I don't know what that looks like in realistic situations. Did you see any enhancement from that?
Yeah, so the way these two effects differ is the typical displacement memory is typically only accumulated during the merger phase, which is when we expect a large amount of the mass to be lost.
Yeah.
But the spin memory, on the other hand, acquires very large contributions during the inspiral phase.
Right. Yes.
And so that fact is directly accountable to what you were saying, where there's a large amount of angular momentum radiated, but it's radiated through the whole inspiral rather than just at the merger phase.
And it all coherently adds. Yeah.
Exactly. Yes. So that's why there's a decent component to the spin memory here seen around time equals 0, but there's also a non-negligible contribution seen at times before that. Yeah. Exactly.
Thank you.
Right. So we have these waveforms generated by CCE, which resolve all the memory effects we know of, essentially. But just to make people aware of this, the SXS collaboration is currently the largest producer of NR waveforms. And we have thousands of waveforms that are publicly available, which have been created using this extrapolation technique. And so, right, this has been years in the making, and it's kind of unfortunate that we have these waveforms without memory. And while we can run CCE really fast, right, so Jordan Moxon at Caltech, along with myself, have made it where we can run the CCE procedure in about 20 to 30 minutes. Many of these waveforms in the catalog don't have the information to run CCE. So the natural question is there some way we can fix the extrapolated waveforms? Right, when we look at this picture, it looks like the extrapolated waveform is exactly equal to the Bondi mass charge term from these balance laws. So could we just compute this energy flux term and just add it on? Well, if we revisit these equations for these 4 terms, what you'll notice by looking at the flux components is that each flux component only depends on the strain and perhaps the news. Whereas the charge terms depend on the Weil scalars, which typically aren't available in our catalog. And so what this means is that indeed, we can just compute these flux terms and try adding them back on to the original extrapolated waveforms to see if we get a reasonable expectation for what the memory should be in these waveforms. And granted, this won't be exact, but it should be a pretty decent approximation. And so one way to check this is by comparing to the memory seen in CCE. So here I again have the 2-0 mode of the strain for an equal mass non-spinning system. In black, I have the original extrapolated waveform, which doesn't have memory. In gray, I have a CCE waveform for the same system. And then in red, I have the extrapolated waveform after we've computed the energy flux term and added it back onto the waveform. And as you can see in the lower plot, the absolute error between CCE and this corrected extrapolated waveform is pretty remarkable. In fact, their relative error is about a fraction of a percent. So naively, it looks like all of these thousands of waveforms in our catalog, which don't have memory, we can just compute a rough estimate of what the expected memory should be and just add it back on. And then we can ask ourselves the same question, but for the spin memory. And unfortunately, things are a little bit different. So for some reason, the extrapolated waveforms capture a non-zero spin memory. And so here again, I have the extrapolated waveform in black and the CCE waveform in gray. And what you'll notice is that the extrapolated waveform still has this bump-like function. It's not just oscillations around zero. But what you also notice is that during this early inspiral phase, what Andy was talking about in terms of acquiring more angular momentum or more angular momentum being radiated, you see that the CCE waveform is slightly larger than extrapolated. And again, for some unknown reason, perhaps due to not solving Einstein's equations or the coordinates being wrong, if we integrate this mode to obtain the net spin memory, the spin memory accumulated in a CCE waveform is about twice that of what's seen in extrapolated. So even though we can correct the displacement memory effect, correcting the spin memory effect isn't really possible unless we have access to the Weyl scalars, which for the current simulations in the catalog, we don't. So,
by the way, as in this discussion, it is crucial to know what you put on the initial null hypersurface u equal 0 or u equal something at the bottom of your CCE extraction, no?
Yes, so that's currently an open problem in CCE. Jordan, Moxon, and I are working on it. And we have a couple ideas, but it turns out it's actually not as important as you would think. And I'm going to get to that kind of right after this section of the talk.
Okay.
Yeah. Right, so to kind of just wrap this section up, we can correct this displacement memory effect using the energy flux term, but we can't really correct the spin memory effect. So if you want to look at spin memory using the waveforms in the catalog, you should take it with a grain of salt, because the values you see are going to be a little bit smaller than what we actually expect. But if you really want to do a study on a certain system, just let me know. I'll run CCE for you and give you a more accurate waveform. But again, right, we've only been comparing modes. It would be nice to have a better understanding of what this improvement by adding the energy flux does more broadly. And so to understand that, we can again return to these BMS balance laws. So again, these balance laws are exactly that. They're balance laws. So they essentially impose a constraint on waveforms. So if we take these four terms coming from the balance laws and we add them all up and we call that variable J, we expect the strain waveforms that we have to obey the constraint H minus J is equal to 0, just saying that the left-hand side and the right-hand side of these BMS balance laws agree. And so what we can do then is we can take this constraint and integrate it over the two spheres to kind of see what the average violation of these balance laws is. So here on the x-axis, I have 13 different binary black hole systems. They start as a equal mass non-spinning, and then equal mass aligned spin with the spin increasing from 20% to 60% of its true value. And then the same thing for anti-aligned spins, a precessing system, a super kick system, and then some mass ratio 4 systems. And the y-axis, this is essentially a relative error between the strain and this quantity J. So it's a measurement of how much we're violating these balance laws. And as you can see in red, the violation by CCE is pretty minimal. It's pretty much on par with the error we have in our numerical simulations, which is good. But if you look at the gray dots, the extrapolated waveforms, the violation is pretty severe. But what you notice is that after we add the energy flux onto these extrapolated waveforms to obtain these black dots, the violation is significantly improved by, on average, 4 orders of magnitude. So even though the extrapolated waveforms aren't as good as the CCE waveforms, it's still a pretty remarkable improvement. And the main reason that there's still some kind of violation compared to CCE is exactly because of what I was talking about regarding spin memory, where it has some spin memory, but it's not as much as we expect to be there due to the BMS balance laws. Okay, so now to get to the point that was just brought up about these initial null hypersurfaces. So here, again, the 2-0 mode of an equal mass non-spinning system. In black, I have an NR waveform from CCE, and in blue, I have a post-Newtonian waveform. And what you would notice is that these two are drastically different. And if you didn't have a good understanding about the BMS group or BMS frames, you might say, okay, again, numerical relativity has failed us. Your waveforms don't match expectations. And this is, again, exactly due to this problem of picking the initial data on that first null hypersurface when we evolve CCE. Ideally, right, we could pick that null hypersurface using PN data, but computing PN expectations of what the metric should look like is actually fairly difficult. So what we can do instead is choose initial data that places our system in a reasonable BMS frame, and then post-process the waveform to place it in an expected BMS frame. And so before I get into that, I just want to say, what does it even mean to kind of map to a certain BMS frame? Well, LIGO and other detectors currently assume that their waveforms are in a center of mass frame with respect to the binary, so that it's not, flying through space or something like that. And so currently, numerical relativity waveforms are, people try to put them in a center of mass frame by taking the coordinates of the black holes and essentially getting a Newtonian center of mass trajectory, and using that Newtonian trajectory to figure out what boost and translation need to be applied to kind of get rid of the center of mass drift. As you might guess, that's, again, kind of a naive procedure, because these coordinate positions of the black holes are going to be highly gauge dependent. And it would make much more sense to kind of correct or map the waveform to its center of mass frame using the waveform itself. And so this is work I just wrapped up, and it should appear on arXiv on Friday. But it turns out there is a very clever way to do this. So what we do is we just take the charge representative of the center of mass transformation. And so this charge here, I'm calling the center of mass charge. It's actually very similar to what Jeffrey presented yesterday, what he called the co-moving center of mass charge. The one thing I want to point out is, in order to make it the true center of mass charge, you just have to divide out by the energy of the system, this 1/gamma MB, where MB is the bonding mass. But essentially what you can do is you can take this charge, fit to it with a degree 1 polynomial, and that'll give you the boost and translation needed to map yourself to the center of mass frame. Okay, so this is great. We can fix the Poincare transformations, but what about the supertranslations? What about the supertranslation freedom? So for that, there's been a great deal of work to kind of understand how the supertranslation freedom should be fixed. It's primarily been accomplished by Dane and Mareski. And so what they came up with is, well, the usual center of mass frame corresponds to having the Bondi-4 momentum having only a temporal component. And this is what we call the rest frame. So we should just kind of extend that idea to Scry and define some kind of charge corresponding to supertranslations. And that charge is called the supermomentum. And so there's many different choices for defining the supermomentum, but the most useful one is called the Mareski supermomentum. And so what I want to point out here is that these first two terms are actually exactly equivalent, or pretty much equivalent to the bonding mass, the psi2 and the sigma times sigma bar dot. But then we add on an extra term, which has no L = 0 or L = 1 components. And this kind of captures the memory effect because it's directly related to the shear. And so we can do the same procedure, right, where we take this function and we essentially try to map it to 0. But there's one thing to note, is that this Mareski supermomentum can never be made exactly 0 due to the memory effect. So if you compute the net change in this Mareski supermomentum and you take advantage of the Bianchi identities to kill off some terms, what you notice is that the net change in the supermomentum is exactly equal to the null memory effect. So as long as there's energy radiated from your system, and hence the memory effect, you can never make this supermomentum exactly 0 over a full range of times. You can make it 0 at a specific time, but not over an interval. And so to map to this super rest frame, or what Moresky called the nice section, there's essentially two options. You can use data from Scry minus, or you can use data from Scry plus. And so if you use data from Scry minus, what you're essentially doing is mapping to the frame that post-Newtonian waveforms are in. Because this essentially says that the initial value of the strain is 0, and it'll change to be some non-zero value after the memory effect. And so this is what LIGO and other detectors expect. So for our numerical relativity waveforms, it makes sense to map them to what's called the PN BMS frame. The other option, this is kind of less explored, but I've recently been looking into it, is that we can also use the data at Scry plus to map to the super rest frame. And this turns out is essential for performing any kind of quasi-normal mode analysis. Because when Tucholsky came up with his Q&M formalism, it's assumed that the black hole is in its own center of mass frame as well as its super rest frame. So really when LIGO does any kind of Q&M analysis to do tests of GR, they should really be mapping their waveforms to the super rest frame. Okay, well, to kind of just give a brief example of what doing these mappings accomplishes for numerical relativity waveforms. Here, I again have these 13 systems. For each system, the left bar is a CCE waveform and the right bar is an extrapolated waveform. And on the y-axis, I'm plotting essentially the relative error between an NR waveform and a PN waveform. So it's essentially showing how well can we get these two waveforms to agree with each other during the early inspiral phase of our black hole merger. And so in red, this is just showing the raw error between the waveforms before we do any kind of alignment. Typically, when people do waveform alignment, they do a time and phase alignment. And so that's shown in these blue curves. And on average, right, you see an improvement of about a factor of 2. But then in green, I'm showing what happens when we fix the full BMS frame of numerical relativity waveforms using this PN waveform. So we fix the supertranslation freedom by requiring that the PN waveform agrees with the NR waveform, and we fix the Poincare transformations using this center of mass transformation. As you can see, when we do this BMS frame alignment, then the improvement between the alignment of NR and PN increases by 3 orders of magnitude. So this will prove essential for doing hybridizations between NR and PN waveforms, which is necessary for detectors because they expect their waveforms to be very long and thus span a larger band in frequency space. So this is kind of just the hybrid results, but to point out the issue I raised earlier, I just want people to focus on the right-hand side where I have the 2-0 mode of a strain waveform. In black, it's the NR waveform, and then the other curves correspond to the PN waveform and the hybrid between the NR and PN. And the blue lines just represent where this hybridization interval is taking place. So before the purple lines, the hybrid is the PN waveform. In between, it's a blend of PN and NR, and afterwards, it's just an NR waveform. But what you notice is after we've done this BMS frame alignment, the value of the NR waveform pretty much perfectly agrees with the PN waveform. So even though there's this ambiguity of picking initial data on the first null hypersurface, we can pretty much just resolve that by post-processing our waveforms to place them in a desired BMS frame. Okay, and then last, I'll just kind of mention what we see with Q&Ms. So here I'm showing the mismatch between the 2-2 mode of an NR waveform and a Q&M model versus the number of overtones, where these overtones are additional frequencies that come into play and allow you to more accurately fit the Q&M model to an NR waveform closer to merging. And so this work was largely put out by Giesler, but he only did this analysis for the black curve, which is for an extrapolated waveform. Here I have the CCE waveforms mismatch in blue, and as you can see, it's pretty terrible. And the reason why is because CCE waveforms, because they capture memory, are kind of in an arbitrary BMS frame, whereas the extrapolated waveforms are closer to the super rest frame. But if we take these CCE waveforms and we map their ring down phase to the super rest frame, then the agreement, or then the mismatch between CCE and the Q&M model actually becomes even better than the extrapolated waveform. And this becomes even more significant for other modes, but this is still currently a preliminary result, and we're still developing a more formal analysis on mapping to the super rest frame using Scry plus data. Okay, so now to kind of just wrap up with detectability of memory. So here I'm showing again these systems. In black, I show the maximum value of the strain. In green, I have the displacement memory. And in red, I have the spin memory scaled by 2 × 10⁻³ So as you can see, on average, the displacement memory is about 25% the maximum value of the strain. And I'll again note that these binaries have been oriented such that the displacement memory achieves its maximal value, which is typically an edge-on orientation. The spin memory, however, you can see is pretty small compared to the displacement memory. So even though we expect a large amount of angular momentum to be radiated, it seems like the spin memory is going to be much harder to detect than the displacement memory. In terms of how we actually detect these things, it's a bit, it won't be easy. So when we think about detecting memory, right, memory is really this zero frequency effect, and interferometers can pretty much have no hope of detecting that zero frequency effect. So instead, what detectors such as LIGO are going to try to do is detect the frequency associated with the energy flux that contributes to the null memory effect. And so to kind of explain what that means, on this plot on the right, in orange and blue, I have the noise curves for LIGO and the Einstein telescope, which is a detector that's new and should be online in a year or so. So in black, this is the 2-2 mode. So as you can see, since the 2-2 mode overlaps with the LIGO curve, it's going to produce a large SNR, which just means it's going to be pretty easy to detect that 2-2 mode. The black dashed line is the full 2-0 mode. And as you can see, it has a larger contribution at higher frequencies, which comes from the quasi-normal modes. Whereas the red curve is pretty much just the energy flux contribution. So if we're to detect gravitational memory, we really just have to detect that red curve. But as you'll notice, the red curve only barely overlaps that orange curve. And so the SNR for the displacement memory effect is about 2. And the SNR for the subleading displacement memory effect, or the spin memory, is about 0.05. So for any individual event, it's going to be very difficult to detect either displacement memory or spin memory. And instead, we're going to have to rely on this method known as stacking. And so the word stacking is a bit misleading. It's not that we're stacking memory signals. So it's not that, space is just continually expanding or contracting. It's that we're stacking SNRs from different detections. So we're stacking the confidence of detecting memory from different detectors. And in order to do this stacking, it turns out that we can not only just resolve memory, but we have to resolve higher order modes of the waveform, because the memory actually changes sign under a certain phase rotation and rotation of the phase at coalescence. And so all this means is that for a certain combination of angles, the memory will pick up a negative sign, whereas the 2-2 mode is invariant. So in order to break this sign degeneracy on the memory, we have to detect higher order modes, such as the L=3 modes, in order to understand what the sign of the memory was. And if we can resolve the sign, then we can coherently add signals from different detectors to increase our odds of detecting memory. And so there's 3 papers that have kind of done an analysis on the detectability of memory. One by Lasky in 2016 after the first detection, and they thought we would find it after 50 events. More recently, there have been papers by Hübner and Boersma in 2019 and 2020. And now it looks like we're going to need about 2,000 events is what Boersma, or is what Hübner found, and Boersma said it was about 1,500. So we still need a lot more events, but with the amount of events we're seeing during each run of LIGO, I'm fairly optimistic that we should see reasonable SNRs for memory in the next coming years or so. And so with that, I just want to wrap up by saying that we can now produce waveforms with memory using CCE. All of the thousands of waveforms in our publicly available catalog can be corrected using this energy flux term from the BMS Balance Laws. We can further test the accuracy of NR waveforms as well as observed waveforms using these BMS Balance Laws. And then it also turns out that now that waveforms have memory, understanding the BMS frame that they're in is critically important for both doing modeling as well as analysis on detected waveforms, such as testing the theory of general relativity using quasi-normal modes. And then lastly, I just also want to say that the detectability estimates actually improve slightly now that we have NR waveforms with memory, because we're no longer trying to get approximate expectations of what the memory should be. And if you'd like to read more about this work, I have 2 papers currently published that you can find at the bottom there. And then again, this new paper, which should be on arXiv on Friday, about how we can fix the BMS frame of numerical relativity waveforms. And with that, I'll just say thank you and happy to take any questions.
Just one small recommendation, please give your slides because, okay, there is a lot of interesting material and we'll need some time to digest it. May I
I was planning on sending them right after this talk to make sure I had everything finalized.
Thank you very much. So thank you for the very interesting talk. I was wondering whether in the hyperbolic motion case, this problem of fixing the BMS frame, it's easier. It looks to me, but I'm not sure.
We actually have only just run hyperbolic encounters in numerical relativity fairly recently. I think I just saw some of the first waveforms maybe a month or 2 ago. And right now it looks like there's actually a fair amount of junk radiation due to this misunderstanding of what the initial data should be. So there's still some things to be resolved there. Again, to kind of fix the BMS frame, we're going to have an understanding of what the PN expectation should be, or we can, do it based on whatever the final section of the waveform looks like. But one thing I do want to note is that just based off these preliminary results, when we look at hyperbolic black hole encounters, the memory we see from those, which is ordinary memory, is actually about 20 times larger than the memory we should see from binary black hole mergers. So in the future, the memory we should, it's a question of how many hyperbolic black hole encounters are there. But in principle, it should be much easier to detect memory from hyperbolic black hole encounters. And so if we want to detect spin memory or center of mass memory, we should really be looking for those kinds of systems.
But in that case, conceptually, I'm not saying numerically, would it be possible to fix the frame at what is called Scri plus minus?
Yeah, I think that should be perfectly reasonable, as long as you understand how the waveform should look. Yeah.
Okay, thank you.
I have a question concerning what you call PN waveforms. You mean these, how were they obtained? By the multipolar post-Minkowskian formalism, which includes all memory effects and, tail and memory, etc., or what? Yeah,
this is just the usual post-Newtonian formalism where all the memory contributions are computed according to the computations of Mark Favada. And so the way we generate this waveform is we essentially get the frequencies of the black holes, the orbital frequencies, and then we use these PN equations to evolve the waveform backward and forward in time using these PN expressions. And these are pretty available in a series of papers. So Mark Favada, like I said, I think has the largest PN order memory contributions, whereas other people, I think we've just gotten up to 4 PN or something for non-memory like effects.
Okay.
And then again, people such as Nichols and Jeffrey have developed PN expectations for spin and center of mass memory as well. Yeah, Andy?
Yeah, I'm surprised I hadn't quite anticipated how big it was going to be.
Yeah.
The displacement merit, and I still don't fully understand how it ends up being so big, but of course that's great. But it also suddenly makes me wonder this business of course you have to get the BMS frames right to actually measure the memory effect, but since it's such a big effect, do you have to get the BMS frames right? Do you have to worry about BMS frames for other kinds of comparison to to between the waveform and the data? You know, measuring. I mean, people are wanting to measure the quasi-normal mode yeah, I mean, if the actual you're saying that the actual waveform is off by 20, the end of that line is off by 20%. You can't just adjust the end of the line by 20% without fixing the whole curve. So I'm suddenly wondering how, yeah, do you have to worry about the BMS frame for the things that have already been done? How did we get away without straightening out the BMS frame if it's a 20% effect? I thought it was smaller for some reason.
Yeah, no, that's a really good question. And so I was surprised to learn that when LIGO does their analyses, they don't even take into account the Poincare frame. So they kind of just assume everything is good and do the comparisons between models and data as is. They don't kind of find a transformation that optimizes the alignment between the two.
And they're presumably, I don't know much about this stuff, but like their algorithm, they're really just computing strictly coordinate invariant data, like file tensors and stuff. Is that?
I mean, it's mostly just the strain, but yeah.
Yeah.
Yeah. So, but in terms of the full BMS frame, because these super translations really only introduce zero frequency effects into the strain, it's not going to matter much for LIGO. So for example, when they detect a waveform with memory, they won't be detecting that initial, right? So if you look here, right? So the PN waveform starts at some fairly large non-zero value. LIGO's not going to be able to detect that non-zero initial value. They're only going to be able to detect the frequency near the merger phase. And so the super translation freedom isn't going to matter until future detectors, where we actually have to be detecting how those super translations change the actual frequencies, the non-zero frequencies of these waveforms. So currently it's not a big issue. The bigger issue is the Poincare frame, but it could be an issue when accuracy is increased.
Yeah. Right. Of course, Poincare is part of the BMS group, but yeah. Right.
On this topic, can I ask more about the LIGO connection here? So LIGO is only measuring the waveform at one point on Square Plus. We're not seeing the full sphere. We're not seeing the full BMS group there. Isn't, as far as LIGO concerned, just the time shift of the LIGO detectors the one thing that is actually observable here?
So if you have enough detectors, right, the different memory you see in each detector can actually teach you things about the binary that you observed. So Ashtekar has actually put out some work on this, showing that not only can you use the oscillations to figure out the parameters of the binary, but you can also use the values of the memory to give you information on the binary. So yeah, right, it's going to be harder to determine these things when everything is very close together on Scribe Plus. But if we could somehow, you know, send detectors way off into space and kind of broaden our angular distribution, then we can get much more accurate readings, either from oscillations or from memory effects.
but we can't. I don't think that the time will be quite a few years off to have detectors a gigaparsec away.
I mean, I'm hoping in my lifetime we have LISA at least, which should be. I mean, LISA should see memory really easily, but. Yeah, I mean, who knows what future detections are going to require.
Okay. You have a few more hands up, Geoffrey.
Yes. Yeah, sorry for the noise earlier. So I have two questions. One is about observability. So as you said, there's no detection around zero frequency. So let's imagine I have a theory different than general relativity. And that theory will predict a displacement memory, which is like 10 times bigger. So at the zero frequency. So and then I will compute the waveform of that model, and then I will compare it to the LIGO data. And then with the LIGO data, so there was no way that there would be a different NR from from ancient gravity. So in that sense, there's no test of GR for the displacement memory of. Is it correct?
No, that's not quite correct, because the displacement memory, right, is going to be sourced by, if it's a binary black hole evolution and your theory isn't too drastically different, it's going to be sourced by something else. So for GR, right, it's sourced by an energy flux. And LIGO is really detecting that energy flux's frequency.
But when
So,
you make the statement, you use the flux balance law of Einstein's equations, right? But if I tell you that the flux balance law is a different flux balance law because there is a scalar field or something else, you can't use the flux balance law for that statement. So I just, the displacement memory is just different than, but then I cannot use the flux balance law because, if I have a different theory, it will mess up that. So
in your new theory, if you want to know how to use memory as a test, you'll have to figure out what contributes to the memory effect and what its frequency is. Or otherwise you'll have to build a detector that can, right? You'll just have to put two rocks in outer space and measure their displacement over time. You essentially will have to have freely falling observers.
Yeah. Okay, but you somehow you use the right-hand side of flux balance law to observe the memory.
Right. So when we are detecting memory, what we're really doing is we're detecting the frequency associated with this JJ term, the second term in the equations. And so if you want to detect your new theory with LIGO, you're going to have to do something similar, where you figure out what is contributing to the memory and what its frequency is. Or otherwise, you're going to have to build a different detector that can actually just measure the displacement between two freely falling observers.
Yeah, okay, I understand partially. And then a very short question about the Bondi momentum. So you said you use a Morishi expression for the Bondi momentum. So why not using just the standard expression for Bondi momentum? What is?
Well, what do you consider the standard expression?
Well, I thought all this expression of Bondi momentum was derived since the work of Bondi in the 60s.
So I think that's typically called the Bondi-Sachs supermomentum. But so like there's a lot. There's like the Dirac supermomentum, which is supertranslation invariant. So that has certain uses. The reason the Miresky supermomentum is really nice is under a supertranslation, its transformation is very straightforward. And so in this paper by Dane and Miresky in, I think, 2002, they came up with a very straightforward iterative technique for solving for the supertranslation to map to the super rest frame at a single point. And so the Miresky supermomentum is typically chosen just because it transforms in a much nicer way than the other supermomentums.
Okay, I have to look at that. Yeah, thanks.
Biswajit?
Yeah, yeah. I have a question about the spin memory. What you are showing that there is some mismatch from the extrapolation, like including the flux of the gravitational radiation and some other thing, right? So like what the point is that, like, if we follow Andy and Sasha's proposal, that like basically the spin memory comes from in the soft expansion the omega to the power 0 term, like in the wave form, which basically turns out to like delta u, like delta function of u is the retarded time, and that's why you are getting a peak near about u equal to 0 or time, right? And after that it like decays and don't give any displacement kind of memory like at infinite time,
right?
And like my proposal is that, like, what we found is that like this is kind of a leading iterative order result, but if we iterative once more, then it turns out that this omega to the power 0 coefficient, whatever Sasha and Andy derive, like Andy have, with this there is also a correction in order g square. G is the Newton's constant, so that also will correct to this order, and like whether like this will resolve this difference of the puzzle, these two difference or not.
Which puzzle? You mean the disagreement between CCE and extrapolated?
Yeah, like whatever the term you are adding to like predicting this spinning memory, this is not the full contribution. There is some extra contribution which also you need to include theoretically.
Well, it's a true, right? So this just falls out of Einstein's equations. The equation we have for the spin memory is just from Einstein.
Right. So yeah, so the proposal is like Einstein's equation, you solve at linearized order for the spinning particles, you will get this waveform omega to the power 0 part. But now if you just like with the spin also, you have this moment a spin independent path, and this spin independent part, if you iterate once again next order, like basically you correct the trajectory and iterate once again, you will find that from there also omega to the power 0 correction will come in the waveform. So like whether
So
like
do you mean like the spin memory essentially inducing a spin memory effect?
no, this actually spin memory is fine. The induced part is just from spin independent part, just from the momenta, but like in higher order in post Minkowskian expansion. And this like, yeah, one easy way to understand this is like, I think like in the next iterative order, one finds log omega. Omega it is frequency in the waveform, and this scale of the omega, if you fix to be 2 omega or 5 omega, depending on which frequency range you are looking at, so that will give a constant term. And you see like this, so log of some constant is order 1 quantity, and that is order g square, and that will correct the leading spin dependent omega to the power 0 piece.
Does it fall off with time though?
No, it will not fall off with time. It is like constant, so it will also contribute to delta u, which is like the peak near u equal to 0 you are finding.
Okay, yeah, that could be interesting to check. I suspect more that there's just a large amount of numerical error with the extrapolated waveforms.
Okay.
I would be surprised if they're just uniquely capturing one term as opposed to just incorrectly capturing all the terms. But it could be something to look into. Yeah, thank you.
Okay, thank you.
Can I come back to the LISA question? So the usual argument is that the memory is so low frequency that it won't show up in the LIGO systems, at least not in the current one. Oh, one thing I think you said perhaps incorrectly, Einstein telescope is not next year. That's at least 1 decade away.
Oh. Thank you for the correction. Yeah, I get them all mixed up in my head. Just had Kagra come out, and
yes. There's just too many of them.
Okay.
But given that LISA is quite a bit lower frequency, I've never thought about this, but would actually the LIGO low mass binary black hole memory, because it's essentially a step function in LISA, show up as a step function in LISA?
Yeah, it should. So I talked to Katerina a bit about this, but I think more work needs to be done to see if LISA will kind of just be crowded by memory signals. I'm not quite sure if it will be an issue, but it's something that needs to be looked into a little bit more. And so I'm hoping that after we have a surrogate model built from CCE, that we can kind of run some of these tests based on the estimated LISA curves.
Yeah, these are sensitivities I thought also several orders of magnitude worse than LIGOs.
Right.
Depending how precisely one plots things, with how many factors of the frequency one multiplies into the plot. So, but that's actually a very worrisome effect, that it's not only the white dwarf binaries that might limit LISA, but binary black hole memory.
Yeah, certainly. And so I don't think anyone's looked into that yet, but it would be interesting.
There's also the LIGO, they're not inertial detectors, they're pendula. So the pendula swing back on a time scale that I think is only a little bit longer than the peak of the waveform, and that erases the memory. The memory effect is for inertial.
Right.
But the LISA, those are inertial, I think. So it seems like a far better place to measure it.
Yeah, but so I was also wondering though if that will cause problems with how you keep everything in sync. I don't know.
Yeah.
I have a question about, at some point you mentioned nice sections of scribe, a la Moresky. Can they be defined geometrically, you know, just not saying I compute this plus this plus this, which is gauge dependent? Is there a characterization of those nice cuts? Geometrical?
Not that I'm aware of, but I'm sure it must exist. At least in the Moresky papers, I don't think they ever really provide a geometric interpretation. Yeah, sorry. So not that I know of, but I would imagine there is a geometrical interpretation.
Because are you saying that you compute things which are not the usual supertranslation higher multiples, but something else, and then you take a frame where they are all vanishing to have only L equals 0 and 1 or something like that?
Right. So we essentially choose the supertranslations such that this Moresky supermomentum only has a L equals 0 component, and all other L components vanish up to the memory effect.
But then would it mean that the usual, let's say, supertranslation supermomentum would be non-zero, would have higher L's?
If so, by usual you mean the Bondi supermomentum?
Yes.
Yes, then it will be non-zero.
Okay, just to clarify.
I see another question by Arlok. And Andy, do you still have your hand up because it's a new hand or is it still the old hand?
Hi, so my question is also about the nice sections actually. So is the nice section is defined as the like a rest frame for the supermomentum, right? Only the U, so is there a way to refine it once we have the generalized BMS? We say that is there a nice section where only the boost memory is present and the spin memory?
Yeah, so currently, right, this hasn't been a point of interest because the generalized or extended BMS groups don't affect numerical waveforms at all. But I have been thinking about, it would be interesting to see how waveforms transform under these super rotations or super boosts. And unfortunately, I think the process of defining a nice section for those groups is going to be much more challenging, right? You're going to have some intuitive notion of what the super angular momentum or super center of mass is. And kind of going along with this alpha ambiguity that Jeffrey was talking about, defining those quantities is also incredibly challenging.
Okay, thanks.
Yeah.
Okay, thank you very much. I don't see any more questions.